Hello, physical science class. This is the 19B section of notes. Chemical changes happen, and this section of slides is going to tell us some evidence. How can we have an idea that a chemical change has happened? So chemical change, substances react to form new substances. When you have a chemical change, you have a reaction that takes place causing new substances to form that were not there already. Chemical reaction, atoms are not destroyed or changed, but just rearranged into different substances. Okay? So a chemical reaction may have occurred if, number one, a solid separates from the liquid mixture of chemicals, right? You pour two substances together. This is clear, this is clear. When you pour them together, now you have these little white snowflake type crystals forming, falling out of solution, right? That may be a sign that a chemical reaction has occurred. Also, visible gas bubbles rapidly bubbling up or exploding out of a burning gas, right? So an example would be you take two substances, you mix them together, they start to fizz, right? Fizz, little bubbles. A chemical reaction may have occurred if the substance's color changes, usually permanently, right? So this is not you adding, Kool-Aid mix to something. This is instead, when you mix two substances together, they change and they become red, or they turn green, or whatever, and it's permanent. The temperature of a mixture may change, right? You mix two ingredients together and they become hot, or they become cold, and or some type of energy is produced, right? If you have a fire starting, right, and you feel heat, that would be an example of a way that you might know a chemical reaction has occurred. Okay, a chemical reaction cannot be undone by physical processes. This takes us way back to the beginning of the year when we were talking about chemical reactions versus physical, right? If we had a piece of paper and we chop it all up into 6 pieces, we can tape those pieces back together. That's a physical change. That's not a chemical reaction, because you can undo it by taping together those pieces, right? In order for us to write properly a chemical equation, we need to think about it like this. We're writing what's happening in real life. We're not just writing what we think takes place. I mean, I guess we could do that, but we would need to write it in a way that's logical. It has to follow the law of conservation of matter, right? When we write a chemical equation, say for example, A plus B is C, the law of conservation of matter would be us adding up all of the grams of matter here, and they have to equal whatever's left over at the end, right? All of these grams over here are going to have to equal these grams over here. Tell what chemicals are present at the beginning and what chemicals are present afterwards, right? Which ones are present at the beginning are going to be before the arrow. Whatever happens during the reaction is going to cause this. This is going to be after, right? We're going to use word equations for this, right? We don't have to write things out in longhand. The beauty of using the symbols from the periodic table is we can write word equations in a shorthand that would be easier, quicker to read and say. Formula equations, right? The left side are going to be the reactants. The right side are the products, right? Whatever you start with, so we had our A plus B and it made C over here. These are going to be your reactants. the things that react together to make our product, right? So reactants on the left side of the arrow, products are on the right side. What we need to do when we're writing our word equations, our symbols, our chemical reactions, we have to show the proper number of atoms, both at the start and at the end. And they have to equal each other. How we're going to balance those is by coefficients. What I mean by coefficients would be like, for example, if I said 4 H2O, right? 4 molecules of water, right? That is a coefficient that comes before my chemical equation for water. To write a balanced word chemical equation, you're going to write first the word equation. Then you're going to change over into the formula, and then you're going to make sure that it's balanced, that the numbers on both sides of the arrows are balanced if they're not already. Okay? We'll come back to that in another slide because I want to make sure you know how to do that. One other thing that we need to be aware of is there are some special symbols. For example, if something's dissolved in water, that's called aqueous. It's abbreviated by AQ. If something's a solid, you could put it in little parentheses an S. If it's a liquid, little parentheses an L. If it's a gas, little parentheses a G. Something else that can happen, right? We talked about how sometimes a solid particle or a precipitate happens as a result of the reaction and it settles by the force of gravity to the bottom of the test tube. That is going to be shown or could be shown by a downward arrow. That means you have a solid product. If you have gas, it means, you know, like stuff is bubbling up. That means you're going to have an upward arrow. Arrows are not put in parentheses. They would just be put afterwards. Like, for example, if I said oxygen gas, right? You could put it that way. The Greek letter delta above the arrow indicates that there are reactants that must be heated, right? So if I go back to my little example here, if I said AB are combined together and we have to add heat, we could do a little shorthand delta sign there to kind of show that, and that's going to give us C, right? Some things are going to be catalysts in a reaction. That means they don't undergo change. They're there when you add them at the beginning of the reaction. They're also there at the end of the reaction. And yet we have to account for them. We have to say that they're there, right? They have to be counted in the process. They just don't undergo change themselves as a result of the process. Thanks. That's the end of the 19B notes.